Hello everyone, my name is Kevin Walter and I'll be taking you through the project I did with my partner, Glorious Msiao. The project involves tuning a pre-trained foundation model on the HLS band dataset. First, before I take you through the codes and workflow, let me make a brief introduction on the model's history and the project's application on real-world scenario. Well, the pre-trained model we are using is the PRIT-V100M Vision Transformer, which was trained on the terabytes of data of the HLS dataset. It is quite useful while dealing with satellite images or images taken from aerial view. In our project, as mentioned before, we fine-tuned this pre-trained model on the HLS band dataset so as to achieve high precision in recognizing band scars and across diverse geographical regions. Well, the model's application has broad potential across various industries, especially in sectors that require real-time analysis of land conditions. By accurately identifying band scars, this tool can provide critical insights into post-disaster recovery, environmental management, and more. Now, let's jump right into our main agenda. So the first thing we do is import the necessary libraries that we'll use throughout the project. Then, using the Teams library, we'll check for a version of the PRIT-V100 model that is pre-trained. And as you can see in the output, we have one. And that is actually great as it makes this model importation step easier than having to load it from the website. The next thing we'll do is create the backbone model by instantiating our PRIT-V100 model from team. Here we also set the number of frames to 1 as we are using images with no timestamp. In this line of code, we check the bands of our pre-trained model. The bands our pre-trained model was trained on, and also the bands our pre-trained model accepts as input. Then we go ahead and define our specific bands that are in our dataset and that our model is likely to respond to. This process of defining the band is crucial because different spectral bands capture unique information about the Earth's surface. And these bands help in accurately detecting land cover changes like band areas through multispectral imagery analysis. Next is where we built our segmentation model. And we use the PRIT-V model as the backbone and ARPANET as our decoder. We move on to the next step where we visualize and load our data. We visualize one data point with its label to confirm the input as expected. And this allows us to detect any issues early, like misaligned data or incorrect formats. Well, in the case of loading our data, we set up a data module, and in our case, we use the generic non-geo segmentation module. This module loads and preprocesses our geospatial data and helps us split the data to training, validation, and test sets. Here we also specify the batch size, which is 10, as our data module also has a data loader in it. The next step is we define the segmentation task. Here we set up the actual task, which is a semantic segmentation. And by defining the model's loss function, learning rate, and optimizer, class weights are added to address class imbalance, as we have samples containing more data points for unburned surfaces as compared to the burned surfaces. This helps the model learn to prioritize minority classes. Then finally, we train our model. The training loop is set up using PyTorch Lightning's trainer, which helps in managing model training with added features like early stopping, logging, and checkpointing. This simplifies the training process while ensuring model improvements are monitored and saved for future use. Then, after we have trained our model, we can now test it and evaluate it. So, testing the model on unseen data allows us for the evaluation of its performance using key metrics like accuracy, F1 score, and Jacquard index. This step is crucial to ensure the model generalizes well to new data, particularly in distinguishing burned from unburned areas. This section of the model evaluates its performance on unseen data, focusing on key metrics that indicates how well it generalizes. Well, here is a breakdown. The multi-class accuracy, the model achieves an accuracy of 96.76%, meaning it correctly identifies burnt and unburnt areas most of the time. The F1 score is a 96.76%, which means the model maintains a good balance between precision and recall. While the multi-class Jacquard index is 83.16%, this measures how closely the predicted and the actual classification match. The test loss is, which is the model's error rate, is 1.82, and this value suggests the model is learning quite well. So before I finish this presentation, I would like to share with you the hyperparameters that I had tuned. Well, we first changed the batch size to 10 and the num workers to 63. We use the ARPANET encoder as the decoder, and also the in channels, we made them equal to 6, and the learning rate was 0.001. We also used the Adam W optimizer and set the weight decay at 0.03, and we measured our loss function using the cross entropy, and we used one GPU as we didn't have a lot of computational resources, but it can be scaled up. One can scale the model to be used in many GPUs, and the epoch size was 21, and we logged after every 2 steps. And lastly, the patience, which is the early stopping callback, we did that at 8. So thank you for watching, and that's all. Bye.